In the assignment I just returned, y'all did a problem about a ripple in a pond, right? We talked about the area of the circle when we knew the rate at which the pond was expanding. So this is really a problem that is deliberately assigned as a lead-in to this idea. If I have two related objects, both of which are changing at the same time, I might ask how the rates of change are related to each other. For example, I've got an inflating balloon. And I might as well make this balloon effectively a sphere, make it a large weather balloon or something. So it doesn't have that teardrop shape that you think of most balloons. It's just a sphere. But if you're going to inflate this balloon, that means you're increasing the volume. But if I increase the volume, then the balloon itself gets larger. And that changes the radius. Since I've got both of those things changing, I might ask how one changes with the other. If you blow up a balloon, you can either do it with your mouth, if you've got a sufficiently small balloon, or you can do it with a pump. Let's assume for a moment that I'm going to use a pump. That pump will deliver 100 cubic centimeters a second. So 100 cubic centimeters. 100 cubic centimeters is a standard water bottle, a fifth of that. So not a huge amount of air. But that's every second. If I start with an empty balloon and I put in 100 cubic centimeters of air, it's going to puff up a bit. The next second, it's going to puff up more. The next second, it's going to puff up more. But each time, as the radius gets bigger, what happens if I'm increasing the volume by the same amount every time? Picture what happens when you blow up a balloon. In the beginning, it blows up fairly quickly, right? But as you continue to inflate it, it only increases in diameter a little bit at a time, even though you're adding the same amount of air each time, because that air has to fill up a larger piece. I am changing the volume of my sphere, but I'm asking you about the radius. That means I need to know something about how those items are related. How does the volume of a sphere relate to its radius?
You increase the volume of radius.
Right, but there's an actual formula that tells me exactly how those two are related, Chase. So I would absolutely like to know, do we know a formula that relates the volume and the radius? Because then I can work out how they're affecting each other.
And four thirds ions or a few.
So that tells me that if I know what the radius is, I know the volume. And vice versa. If I know what the volume is, I know what the radius is, right? I can solve for either one. But the underlined item, air goes in, that's not volume. Look at the units on that. That's volume per time, which means that this number 100 isn't a volume. It's a change in volume. It's a derivative. And it's not just any derivative. It's the derivative of v with respect to time because it's cubic centimeters per second. Now that means that over here in this equation, v is a function of t, but there's no t's over there on the right-hand side. There's only an r over there on the right-hand side. If the volume should be a function of time, then something else needs to be a function of time as well. And that's exactly what this is telling me. I want to know how the radius is changing. That means that the radius is also a function of time. And that means that what I'm looking for over here is the change in the radius. Now, I don't know personally of very many situations where I need to know how fast the radius of my balloon is changing as I push more air into it, except one. In California, no, I've forgotten what year it was. Look up Highway 880 on your internet device. Highway 880 in California. I think that's the right number. Interstate 880 in California. What's interesting about this highway? Instead of having two roads next to each other, an eastbound lane and a westbound lane, it has one road on top of the other. It's stacked. And it goes through the middle of Oakland, California. And in 1989, there was an earthquake. What do you think happened to the road? Layer 2 collapsed onto layer 1. A large number of people were trapped in their cars in the middle of this. They threaded balloons into the wreckage, into these cars, and inflated them to try and separate the layers of concrete. But they couldn't move too fast because the concrete moved too fast, it would crack and fall back down. So they had to know how fast the radius was changing as they changed the volume. This problem that I had pulled out of the textbook was completely made up bullshit. It was really used in 1989. Okay. How do I find this? How do I find dr dt when there's no t's in this problem? I'm going to use implicit derivatives. I'm going to use my chain rule. And I'm really going to think of this equation right here as v of t equals 4/3 pi r of t cubed. See the chain rule going on over here on the right? If I take the derivative with respect to t, then on the left, I get dv dt. What do I get on the right? What happens with this? Except that I need to do, because it's a thing cubed, I need to do the chain rule in there, right? So the 4/3 of the pi, they're numbers, they just stay there. Constants that are multiplied stay multiplied. But now I have ugly cubed. It's derivative of ugly cubed. And then the chain rule comes into play, Dean, and here's where I get dr dt. Now, you don't actually have to write r of t. You don't actually have to write v of t. You could go directly from this expression up here to dv dt was 4/3 pi 3r squared dr dt. But then I'm thinking about r as having t's hiding in it. I'm thinking about v as having t's hiding in it. And I didn't bring my little nesting doll, so I can't rattle it at you. But I want to hear that noise in the back of my head. I'm doing the chain rule. There's something on the inside. Oh, wait a minute. What am I trying to find? Says right up there, I want something. What is it I want? Which means I want dr dt. If that's the thing I want, I should know all the other numbers and be able to plug them in. Do I know dv dt? Yeah, I was told exactly how fast the volume is changing. Do I know r? How? Because it says up here that the diameter of the balloon is 50 centimeters. Well, that means I know this. I know this. This is the only thing I don't know. I can solve for it. Please notice that this 3 down here and this 3 up here, they're canceling. So I'm going to get 100 is 4 pi times 25 squared dr dt. You can tell me what dr dt is now, can't you? Wait a minute, 4 times 25 is 100, isn't it? So the 4 and 1 of the 25s on the bottom will cancel with the 100 on top. This is the same as 1 over 25 pi. If you want to give me a decimal, that's fine. Matter of fact, you probably should, so I have a number to hang my hat on here. What is this as a decimal?
Six, 37.
Did you have parentheses on the bottom? Then what you did was 1 over 25 times pi, unfortunately. You got to keep those parentheses because the pi is on the bottom. Huh. What are the units on this number? Oh, time for Quant Lab. Let's do our unit calculation. What are the units on this number? I don't even have to have the decimal to know what the units are. What pieces of this have units? Two of the numbers in that expression have units on them. Okay. So what are the units on the 100?
Centimeters cubed per second.
And what are the units on the 25? But then that'll be inside the square, right? What happens to my units? So I get centimeters per second. And does that make sense? Does that unit make sense? Well, that's how fast a radius is measured in centimeters, would be going. Ah, found the right answer. Now, this is 0.01 centimeters per second. That's really, really slow. But our balloon was already 50 centimeters across. 50 centimeters is 21 inches. About that distance. Where was the biggest problem in this whole setup? Biggest problem wasn't in doing the calculus. All I did was take one derivative, and it was power rule and chain rule. That was the easy part. The hard part was figuring out the relationship I wanted to work with in the first place. One of the biggest difficulties we will come up with in doing these sorts of change-related problems is trying to figure out how to set up the things that are changing so that I can understand what's going on. Question? of a ladder leaning up against the wall, 10 foot long. And all of a sudden, the bottom starts to slide out. Oh, forgot a piece of information. Wall, when the bottom is 6 feet from the wall. So I need you to picture this, and a crappy picture helps. So let's draw a crappy picture. I have a wall, I have a floor, and I have a ladder. There we go. What's happening dynamically? What's changing in this picture?
Oh, ladder, height.
So the ladder is going to slide down the wall, right? The bottom is going to go to the right. The top is going to go down. So as this point is going this way, this point goes that way. The ladder itself does not change size. It doesn't bend. It doesn't extend. It doesn't shrink. It just slides. Huh. Okay. So two different things are changing. I should label those two things. I'm going to label the distance across the floor and I'll label the distance on the wall. What do you want to label them? Okay, so this distance right here, that will be F, and this distance right here, that will be W. And I know both of those things are changing. So somewhere I should have a dw dt or a df dt, and I should be wanting to find one or the other. Because it does ask me how fast something is happening. How fast is what changing? Which means I'm looking at the change in W. So this piece right here, that tells me I want the change in W. There are two other pieces of information up here, well, three other pieces of information up here that will probably be helpful. I've got three other numbers. Hopefully they all come into use. Nothing's thrown up here as a red herring. Do you want to deal with the 6, the 1, or the 10 first? Those are the three numbers that are on the wall, on the screen. Because none of them are on the wall. The 1. So what's the 1 represent? It's the change in the bottom of the ladder. So that's df dt. Okay. I need some more information. What about the 6 or the 10? Which is which do you want to do with next?
Six.
So what is the 6? It's when the bottom is 6 feet from the wall, which variable does that go with? Aha. The only other piece of information I have is that the ladder is 10 feet long. That doesn't go with either F or W. That goes with the ladder itself, right? I should put units on these. This is feet, this is feet, this is feet per second. Hmm. What relationship, geometry, algebra, what relationship can I use to relate F and W? Pythagoras, because that's a right triangle. At least I'm assuming the building is nice and square, right? So if this is a right angle, then by Pythagoras, I know that F squared plus W squared is 10 squared because the ladder doesn't change. F and W change, but the ladder doesn't. Okay. F is changing in time. W is changing in time. The ladder doesn't change ever. I can take the derivative in time right here. If I do that, what happens on the right-hand side? Right-hand side's a number. What's the derivative of a number? Zero. But those other two things are changing in time, so I need to think chain rule. Rattle, 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 rattle. What's the derivative of F squared? But wait, there's more. Because that's the derivative with respect to F. And I want the derivative with respect to T. What does the chain rule tell me I need? I need a df dt. How about W squared? The exact same idea. Now, I say to myself, the thing I am trying to find is, so let's get that all alone. Get dw dt alone. Little bit of algebra, I move the f df and t from the left side to the right side, that makes it negative. Cancel the 2's and then divide by w. If I know the numbers that go into the right-hand side, I'm done. Do you know f? Do you know df dt? Do you know w? It was Dean? Is it just? Right, I don't have W up here on my picture, right? I have F, I have the F to T, I don't have W, but I can use Pythagoras to get it. F was 6, the ladder is 10. So that means that W squared is 100 minus 6 squared is 36. 100 minus 36 is 64. What's W? There we go. Oh, wait a minute. 6, 8, 10. That's a 3, 4, 5 triangle. If I'd recognized that, I might not have even need to do Pythagoras, but I can't count on always remembering all my primitive Pythagorean triples. So now I know all the numbers that go into this side. dW dt is minus F over W times dF dt. Minus 6 over 8 times 1 is negative 0.75. Yes, sir.
Well, how does DFDT, you just, that doesn't say in the numerator, but you divide W.
Oh, it could be. It could be in the numerator. It's the same thing, right? Because I'd multiply on top. 6 times 1 divided by 8. I did 6 divided by 8, then multiplied by 1. What are the units on this number? Because here I have feet for 6, feet for 8, and feet per second for df dt. So this must also be in feet per second. First question. Does this number make sense? Is F getting bigger or smaller? F. Is F getting bigger or smaller? Because we were sliding away. W is getting smaller, so the change in W should be negative. If it's from a bigger number to a smaller number. This does make sense to be negative. And if the bottom was 6 feet away and the top was 8 feet away, then the bottom would move more than the top to keep the ladder the same length. So being smaller than 1 makes more sense here. Page 249. I have this general problem-solving strategy for this type of problem. Please notice the first step. Read the problem carefully. I actually have a 0th step. Read the problem without making any notes at all. Then read the problem again and make notes of the things you are told about. And that's really draw a diagram and introduce notation. Those two pieces are making the notes. We drew the picture of the wall and the ladder and the sliding. We drew the picture of the balloon. We thought about what it meant, the radius and the volume. Then we gave some notation, F and W. I did this problem in my notes. I did it in X and Y. But I labeled my diagram with X and Y, so I knew what was what. So what you called F, I called X, but it worked out exactly the same way. Exact same calculation. Once you've got anything that changes, anything that is a function of time is something that changes. Those have to be variables so I can keep track of what's changing. Then find some rate behavior, those are derivatives. Anything that's a rate, name it, make it a derivative. If it's something you don't know yet, that's probably the thing we're to look for, or we have to find along the way. Find your equation. This is where things go a little crazy. Because depending on the situation of the problem, you may need facts from geometry. You may need facts from business. You may need facts from physics, from chemistry. You may need information not explicitly given in the problem all the time. Sometimes you need to know some basic pieces like the volume of a sphere, the volume of a box, the volume of a cone. And then I'm going to take my derivative using the chain rule. Put in the information I know, figure out if I need any extra, and let's solve for the thing we're looking for. This is the reason I said we might need some more geometry ideas. Here is a water tank. It's an upside down cone. I don't know if you know the formula for the volume of a cone. The volume of a cone is 1/3 the volume of the cylinder that contains it. A cylinder. Hang on a second. What's the formula for a volume of a cylinder? It's the base, which is a circle, times the height. So the formula for the volume of a cone is 1/3 the base circle, pi r squared, times the height. And what we're asked to find out in this problem, I know I'm pouring water into this tank at a given rate. Find the rate at which the water level is rising. How fast is it going up? If you put in the same amount of water when we're down here, you're going to get a lot larger of an increase than when you put it in up here, aren't you? Because this tank gets wider as you get closer to the top, so the water rising slows down. But without this formula, I'd be at a complete loss on how to do this problem. I'm not going to go through this one. It requires you to use some geometry pieces to get it right. You should absolutely read this problem carefully. Instead, I'm going to jump over here. Here are a bunch of other problems we can do. If you look at 29, 29 involves cone as well. I got gravel coming up in a pile. Let's look over here at 22. A boat is being pulled into a dock by a rope attached to the bow of the boat, passing through a pulley on the dock that is 1 meter higher than the bow of the boat. The rope is pulled in at 1 meter per second. How fast is the boat moving? When it's 8 meters from the dock. All right. They've given me a picture. I'm going to make a bad copy of it. So at least I have a starting point. I have my boat. The rope is tied to the front of the boat. The rope goes up to a pulley on the dock. Somebody is here pulling the rope. Okay. I was told how fast the rope is being pulled. How fast is the rope being pulled? 1 meter per second. And I was told that the boat is 8 meters from the dock. I was also told something else about the dock. What else was I told about the dock? Problem 22. The height of the dock. I was told that the dock is 1 meter high. Gee, what do I see again? Technically, Chase, I think I misspoke. I was not told that the dock was 1 meter high. I was told that the pulley was 1 meter above the bow of the boat. So the dock might actually be higher because it's got to go down to the water to where the boat is. But the distance from the pulley to the top of the boat is 1 meter. I see another right triangle. So I have this sinking feeling that I'm going to use Pythagoras again. But let's think about what we want to know in terms of what is changing. What things do I know are changing in this problem? Okay, so I need a letter for that. If it's changing, it's got to have a variable. So R for rope. R for rope. And if that's R, then what's this? That's going to be the change in R. Now, is the rope getting bigger or smaller? So should the change be positive or negative? You could leave it positive and use the word shrinking or use the word decreasing. If you make it negative, then you've built that into the sign. You don't have to make it negative, but I think it would be better if I made that a -1 to indicate, hey, this rope is getting smaller. What else is changing? We don't know how fast the boat is going, do we? But that might be something I'm interested in figuring out, right? What are the units of the boat's speed? It'd be meters per second. I'm measuring stuff in meters. Speed would be meters per second. But that means something for the boat in meters has to be changing. I haven't labeled anything for the boat, have I? So I need a label for this horizontal distance here. I don't want to use D because I keep using D over here for derivative. So I need something else. We call it B for boat. Okay. So if this is B for the boat, right now I know B equals 8. But the thing I'm looking for is the speed of the boat. Given that this is another right triangle, I should think about the relationships I've got for right triangles. And once again, my favorite Greek geek bumps into my head. I should use something with Pythagoras here, shouldn't I? If I'm going to use something with Pythagoras here, I need to write that something in terms of both these variables that we've just created and with whatever numbers we got. Make sense? In our case, because this is a right triangle, b squared plus, oh, we didn't give a variable to this, did we? Because the dock isn't moving. It doesn't need a variable. It's always 1 meter up. Since that piece isn't changing, I don't have to worry about its derivative. Just like we did in the previous problem where we knew the floor but didn't know the wall. I know right now the boat distance, but I don't know the rope distance. If I do my derivative, take my derivative here, what do you get? plus 0, because that's a number, equals and yes, I would be more than happy to let you use B prime or R prime. But the reason I keep using dBdt and drdt is to remind myself these are changes in time. So I want to keep that emphasis in my head for the situation I'm dealing with. Clearly, I'm trying to find dBdt. I'm going to need R to do it. I don't have R. I got to go back here to find R. At the time that the boat is 8 meters away is what I was asked for. Unfortunately, this gives me R squared is not a number with a nice square root. So I get R is the square root of 65, which is unfortunate, but makes enough sense. It's a little bit bigger than 8. Well, now, I'm sorry, I have B and dr dt. I don't have dBdt. I'm looking for dBdt. My apologies. I wrote the wrong thing. But that means I can put all of these numbers in here now. 2 times 8 times dBdt, that's the thing I want that I don't know yet, equals 2 times R times dr dt. And so I can get dBdt all alone. The 2's cancel, and I get dBdt is negative root 65 over 8 meters per second. Which means even though I'm only pulling at 1 meter per second, I'm actually having the boat move faster than that, because this number is roughly 1.008 meters per second. I'm pulling at an angle, so I'm moving a little faster than the rate I pull up at. Questions? Again, I will ask, does the fact that this is negative make sense in our problem? Why, Jules? And so the change in length should be making it get less. Again, depending on the problem you are looking at. Look at problem 20. Why is it easier to steal second than steal third? Because if you throw it to the catcher and you're stealing the base, then it doesn't get hit. And it takes longer to throw to second than it does to third, right? But if I hit a fly all the way to center field, I can work out how fast I have to move to beat that fly back in, don't I? To cover that 90 feet in the appropriate time. I need to know, again, some geometry to be able to solve this problem. Here's our gas law problem, problem 37. Here's some electricity problems based on resistance, which you may or may not have taken a physics course that involves electricity. Maybe, maybe not, but they give me the rule that I need so that I can use it. Here's one about force. I've got a pulley pulling one to the other. How's the force change? 32. A kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string is let out? Allow me to be one of the first people to tell you that this problem sounds absolutely stupid. This sounds like a real joke. Why the hell would you care how fast the angle is changing? I'm going to turn this problem 90 degrees. We're actually going to do the one that's written up here, but I want you to think about this for a second. I have a rocket going up. How do I communicate with people in that rocket? With a radio. I can't exactly just call them on the phone. There's no what. I got to get a signal to them, right? In order to escape Earth's gravity, do you know how fast you have to be going? You have to be going 7 miles per second. 420 miles. Sorry. No, I'm going to screw up the conversion. 420 miles a minute. I gotta move fast. I got a radio I gotta keep in touch with. I've got to track that radio with a satellite that's on the ground. Where do rockets get launched from in America? Which is where? Cape Canaveral, Florida. Florida's good enough. It's actually a little further south than Daytona, but it's in that section of Florida. But where's mission control? Mission control is not in Cape Canaveral. Mission control is in Houston, Texas, 930 miles away. So the radio that's talking to the rocket is coming from Texas. So it's got to track as that rocket goes up. It's got to adjust its angle. Useless crap. I'm never going to worry about a kite traveling horizontally. I'm really going to be concerned about a rocket going up and being able to talk to those people. Let's solve this problem. A kite 100 feet above the ground moves horizontally at 8 feet per second. At what rate is the angle between the string and horizontal decreasing when 200 feet of string has been let out? Time for a crappy picture. A kite is traveling horizontally at a speed of 8 feet per second. The angle between the string and the ground is decreasing. Now, I've drawn this kite moving to the right. I need you to tell me where the person with the string is standing. Are they over here on the left of the kite? Or are they over on the right of the kite? The kite is moving from left to right. Which way would I be going to make the angle get smaller? You're going this way. So I need to be standing way over there, because if I'm standing on the right side, the angle's going to get bigger. So I've got to be over here on the left in the picture. Human being holding string. The angle between the string and the horizontal. Okay. That's a crappy drawing. I'm good with that. What other information was I told about this kite? 100 feet off the ground or 100 feet. Okay. Height of 100 feet. Height 100 feet. Okay. I suppose if I really want to be technical about it, I put the rope on the ground and I'm standing on it with my foot as opposed to holding it in my hand 5 feet up. What else was I told about this kite? I want to know how fast the angle is changing. Let me write that down. I want the change in the angle when what? Which means I need a variable for string. S for string, and that'll be 200 feet. Once again, I am happy to say I have a right triangle. So I know two of the sides of my right triangle means I could find the third, couldn't I? I haven't given a label to the third. What do you want to call that horizontal distance there so that we can give it a name? I want to use distance because that'll be a D, but I'll use length. So if I go from here to here, that'll be length. L. I don't know what L is at the moment, but I can find out, can't I? How do I find L? Say again? Pythagoras again. So L squared plus 100 squared is 200 squared. Well, 100 squared is 10,000 and 200 squared is 40,000. So L squared is 30,000. Which means I can take the square root. L is the square root of 30,000, which is 173.2. I also will note that I have a number that doesn't have a variable on it. All the way up there, 8. What thing is that 8? Unfortunately, no. Because that doesn't tell me about the string changing, because the string is at an angle. It's telling me that that is horizontal. That's actually the change in L. And that's the reason I know the angle is going down. Because if the string was getting longer, wouldn't the angle just stay the same? But if the string is at 200, then this kite is still moving, then it's got to go down to adjust for that. It's a good thing I've flown a kite. I know how they work. Okay. That's great. That's useful information. I don't have diddly squat up there about theta. Ah, crap, I got to change classes. I can't use Pythagoras. Pythagoras is all about sides. If I'm going to do stuff about angles, I need my trig class. Or maybe I am letting string out, but the kite is still moving. But since the kite is only moving horizontally and not out, S, I don't know how S is changing. I don't know. I don't have anything about ds to t. Would be nice if I did. But having dl dt makes this work. If I hadn't had the word horizontally, then I'd have a problem. Trig functions. I need trig functions that involve the things that I know the change about. Well, I know how fast this side is changing. I don't know how fast this side is changing. So I can't use any of the trig functions that involve the hypotenuse. That really only leaves me two trig functions. Which two trig functions do not involve the hypotenuse? Say again, Dean? Tangent and cotangent. Might as well use tangent. Tangent's easier. Tangent is which two sides? Opposite and adjacent. In this case, that's the opposite side and that's the adjacent side. So I know tangent of theta is h over L. But I know h doesn't change. So this could be written as 100 over L. Or if you'd rather, you could write it as tangent theta is 100 L to the negative 1. Now here's the best part. That is going to be something that if I take the derivative on the left, I'm going to get something with a d theta dt. If I take the derivative on the right, I'm going to get a dl dt. And those are things I know. So let's do our derivatives. What is the derivative of tangent of theta? I have to go back to my trig functions list, which is on our review sheet. It's on the formula sheet you're going to get. It's in chapter 3, section 4, section 3. I don't remember. But you can look that up. What is the derivative of tangent of theta? Open your textbook, open your Canvas page, open your notes if you took a picture of it off the screen. If you printed it out like I told you to last week. Derivative of tangent. Exactly. The derivative of tangent is secant squared theta. So over here, derivative of tangent theta is secant squared theta. But wait, there's more. My chain rule says d theta dt. On the right, what is the derivative of 100 L to the negative 1? But wait, there's more. Exactly. Now here's the interesting part. I know L. Right there, I even know L squared. And that negative 2 means it's on the bottom, squared. I absolutely know L. Check. Do I know dl dt? Yep, that came right from my picture. I'm looking for d theta dt. It says right here, I want d theta dt, which means I need to know secant squared theta. Now you might think that means I need to know theta, but you'd be incorrect there. Because I can build secant from knowing the sides of my right triangle. What other trig function is secant related to? Out of the basic three, sine, cosine, tangent. It's 1 over cosine. So I can write secant squared is 1 over cosine squared, right? I'm going to move that cosine from the left side to the right side. D theta dt is minus 100 over L squared dl dt times cosine squared theta. And now I just need to figure out what the hell cosine is. But here's where I get to say, I know what cosine is. I'm going to make a quick, dirty copy of my triangle. This is S and L and H. What two pieces make up cosine? Which in our case is L and S, right? And it's squared. I don't actually need. Eek, wrote the wrong thing. That's not over H. That's over S. I wrote hypotenuse. But I know those numbers, don't I? Adjacent over hypotenuse. What's L? Wait a minute. Hang on a second. This is going to be squared, right? And then make it L squared on top. And that cancel with the L squared over here. Oh, you sneaky person, you. Minus 100 over L squared dl dt, L squared over S squared. Those cancel. What was S? And dl dt? Minus 100 times 8 over 200 squared. That's d theta dt. Which, by the way, simplifies. Minus 800 over 40,000 is negative 1 over 50, which is negative 0.02. Okay, hang on a second. What are the units on this number? Unfortunately, no. I never mentioned degrees anywhere in this problem, did I? And I'm a math geek. What do I use instead of degrees? It's radians per second. If I'm dealing with a trig function, unless I have the right conversion factor in place, I have to be dealing in radians. If I'm given something in degrees per second, I'll need to switch it. So as much as I like the idea of saying 2 degrees a second, that doesn't help me when I go to use trig functions, because trig functions built in radians. Okay, that was a stretch, wasn't it? Even though it was a right triangle, I couldn't just use Pythagoras. I needed some trig pieces floating in there as well. I did at one point, a number of years ago, ask a problem that didn't involve a right triangle at all. Which means I need a rule that is like Pythagoras, but for triangles that aren't right. Now, I am going to stretch you back to your pre-calculus class and say that if you're not dealing with a right triangle, you need a different rule, and that rule is the law of cosines. So please do me a favor and go look that one up, because you'll use it in this section. Questions? I have been told by students repeatedly in the past that the biggest problem with this section of text is not the calculus we are doing. It's the setup and the external to calculus knowledge I'm going to need. Whether that's trig, chemistry, physics, geometry, I'm going to need something, not just from this course. That's the reason we're at a liberal arts school, so we get all this other crap in here too. I will see you all tomorrow. Have a wonderful rest of your day.